Well, hello everybody. Strange setting today, having a lecture without any physically present audience, but let's see how we're going to do that. I will record approximately 1 hour now for my talk, which is entitled Reducing Environmental Side Effects of Blasting and Quantifying the Output, Improving Mining Performance by Measurement. So measurement is very important here. And I will record this talk for about 1 hour now, and then afterwards there will be time for question and answer session, hopefully live then through the online portal and stream. Well, first of all, I want to start with this statement by Lord Kelvin. He said, when you can measure what you're speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. So that's the reason why we want to measure things. We want to know things about the process, we want to know what's going on, and when we want to push this in numbers, or put this in numbers, and not just say, okay, my belly told me that, it should be the other way around. So we want to know what we're talking about. First of all, a couple of words also about myself. So my name is Phillip Hartlieb. I'm a senior scientist at the chair of mining engineering at Universität Leoben in Austria. And as you can read here, my major research areas are all about rock fragmentation, so drilling and blasting, but also mechanical rock fragmentation, alternative rock fragmentation methods, a bit of digitalization in mining, which is, well, a mixture of the talk today, digitalization and blasting, and some of the other things as well. So, well, that's me, but let's go into the topic quite quickly. What I'm going to present you, a couple of things. First of all, the definition of key parameters, because when we measure something, we want to know which parameters do we measure, and what do these parameters mean for our later life or our later assessment. And then I will detail two very important things. That's number one, the automatic blast design software. So based on the measurements, based on the data that we have, how can we improve a blast, and what is an improved blast, first of all. And secondly, also the assessment of blasting work on the basis of KPIs. So the key parameters, as I said, we want to measure them, we want to analyze them, and derive our conclusions in the end. So that will be the last point of this presentation. I will rely or set up most of the presentation on a specific use case. This use case was recorded on the Erzberg mine, which is the largest hard rock open pit in Central Europe. It's very close to Leoben in Austria. And yeah, what we did there, it's an open pit mine, it's a long history. And the three subsequent points are most important. So it's situated close to the city center. So you see the city center is here in the lower area. It's in the middle of the Austrian Alps. You see the very nice panorama here. And due to the city center and some other facilities and touristic facilities in this part of the vicinity of the mine, it's close to neighbors. And you can imagine whenever you have a mining operation close to neighbors, close to tourist attractions, well, there are some conflicts in terms of noise, vibrations, whatever you can think of. And that's what we want to improve and what we want to make better in the future. So as I said, number one, we have to define our key parameters. So what do we want to investigate? Which kind of data do we want to measure? From which kind of data do we want to derive our conclusions? So the key parameters that we are talking about is, well, of course, the first thing is you can talk about them before blasting. So that's the blast planning, that's the geometry, the drilling accuracy. Then we have parameters of the explosives, so which type of explosive, with density, which detonation velocity, and the geological influence, of course, is also very important. So how many faults are there? How are the structures that are in the rock? And of course, these are just 5. You can come up with many more that you can assess before blasting. But I think these are the 5 most important parameters that you can also easily assess and easily, well, put in numbers whenever you have blast. Secondly, of course, and that's probably for the neighbors, is the most important. For neighbors, for the neighbors, this is the most important blast, the things that you can measure during the blasting. First of all, the delay timing. That's nothing that the neighbors will feel directly, but that's what influences all your processes. Then the flow of the material. So you want to know how does the muck pile look like afterwards? How far do the pieces of rock fall, or how far they've thrown? And then, of course, we have vibrations, we have dust, we have noise that is generated from a blasting site. And that's something that we want to measure during the blast. And last but not least, what is most important for the mining operations is what happens, what happens after blasting. So after blasting, it is very important to know how does, my result look like. How is the blasting volume? How are the grain sizes? So what's the grain size distribution? You can imagine that grain size distribution will change depending on your blasting setup, depending on spacing, burden, delay times, the amount of explosives that you have in your drill hole. Then something that many people want to find out, but only few people really manage is, for example, the loadability. So how easy is it to dig material, how easy is it to excavate the material afterwards? How much energy consumption do you, for example, have in the crusher there, depending on the grain size distribution, depending on the characteristics of the muck pile. So these are, short summary of all the parameters that we want to measure and that we can measure. And now we go a bit into detail about how we can influence the blasting site based on these parameters and based on the input parameters. So I will talk a bit about the blast design and a bit about the blast analysis, the direct blast analysis and not the analysis of the mine. This will be subsequent, the second part of this presentation. So we will talk about the placement of boreholes, hopefully automatic. And also the characterization of the rock mass, automatic, and of course the characterization of the rock mass will influence the placement of the boreholes. Because if you know how the rock mass is structured, you have more information of how to place your borehole. And then of course you want to know about the muck pile, how does it look like, what's the grain size distribution, and that's also something that the software can do quite good for you. Number one, and I hope you can see this little drone flying up in the air. Number one, we have a drone, for example. This UAV takes pictures. That's what you see on this right-hand side. And it takes the pictures for a certain purpose, because you want to generate a 3D model from your blast site. You want to know how the blast site looks like. That's something that you can see here. You have a 3D image of your blast site, which is nowadays state of the art. I think you can do this easily with off-the-shelf software in the end, off-the-shelf drones. Of course, it would be a matter of the precision there and the ease of handling of how professional your drone is, but you can do this rather easily. What you can see here on this graph, for example, is an upcoming blast site. On the back end, you have this white heat, which should represent the drill holes. And you have a profile line here, which, gives you some information on the blast. But what you can really do with this 3D information is not just having a nice picture of a blast site, it's digging into the detail and really seeing what is behind that. And this picture is a bit of a better resolution, or scroll down of the same picture as before. But what you also have in this picture is you have the position of the drill holes, which are associated to that blast site. So for every drill hole, you know, I hope you can see this with the camera, you have the red line here, which is the actual position of the drill hole, and you have the black line here, which is the actual face of your bench. And for every drill hole, you know how far is the bench spaced from the drill hole, so how much burden do you have at which specific part of your face. And you can see this down on this picture that there's a color coding there. areas, blue areas, green areas, red areas. And with this color coding, you can very easily see where is the burden too high, where is it too low, where is the burden in a complicated or not so good situation. And then, of course, you can react with the drill planning or with the blast planning on that. You can react saying, okay, I need more explosives, I need less explosives, I need probably different types of explosives, or I need to take special precautions and special care for this blast. Yeah, as an example then, the blast design software, for example, could also place your blasts, or the drill hose in the optimum way for optimum burden, optimum spacing, so that you avoid any pitfalls in this geometrical situation. As you all might know, that for example, when you have too little burden and too many explosives, everything will be thrown away. If you have too high burden and too little explosive, you will just generate vibrations and nothing else will happen. So the truth or the best solution is somewhere in between those. That's why you want to make sure that everything is done in the best possible, the best feasible way. Well, this is the example. You can then really see that this is all blue and green and quite good way and good way forward. Another thing that you can do with measurement, with automated measurement, is, for example, analyze the geomechanical or the geological situation automatically. So this is just an example where the software analyzes the surface of this upper right triangle or rectangle here. And if you can identify those surface normals, you will come up with plots like that, and you know then the structures and the dominant structures in your rock, and you know how the situation is and which faults are important for you and which ain't. You can also, it's the same picture but with a bit of different coding. You can also identify a certain range of joint sets. So you have the red ones, you have the yellow ones, the green ones, the blue ones. And this is also represented here on this slide. So you see where the orientation of the red fault joint set. You see the orientation of the blue, the pink, the green, and the yellow joint set. And with that, you can improve your understanding of the situation and your planning capacity. And now imagine, for example, that a geologist would have to go to this blast site every time you do blasting and do all the mapping, which is huge effort. And the software like that and automation like that can help your geologist in understanding the situation and in mapping that quickly and reliably also for your operation, so that you can change on a daily basis. So the mine that we have been testing this is, well, they're blasting every day, so you can't take a lot of time to do your planning there. So now we did the blast design, we blasted, we know what happens. The second part of that will be the blast analysis. So we want to know what's the outcome of the blast, what did we do to the rock, and is it good for us? Also here you can see a picture that is hopefully changing over time. You can compare how the situation looks before the blast, after the blast, and after mucking away the rock pile. And then in this example, you can see the yellow part. This is the volume that you actually extracted. In this case, it's roughly 60,000 cubic meters. And there's one thing where all the automation can't help you, which is very apparent in this picture. That's this kind of moon-shaped part, because there the guy who was taking the picture was slower than the wheel loader driver. So the picture was taken after the wheel loader driver has already excavated the first couple of shovels. So the result in that sense will not be true here, but of course a good way in the right direction. So, well, best technology doesn't work if you don't coordinate your approach properly or your operation properly. Take care of that. Well, what you can also do, you have seen a very similar picture a couple of slides ago. You can compare the pre and the post blast. You can see where the macropile is, how it looks like, how the shape looks like, and this, of course, helps you in understanding the future or planning the future. So you understand the past, you know what's going to what you have to change. Sorry, what you have to change for the next blast and for the future operations. Something else, for example, would be the swelling of the macropile. Also here, you can analyze how the volume was before the blasting, how the volume was just the bank volume. So the solid, this would be the solid volume before blasting. This would be the macropile after blasting, and you know this would be 12,000 something cubic meters. This would be 18,000 cubic meters. So the swelling factor would be roughly 1.5. So you have 1.5 times more volume than you had previously, simply due to, well, fragmentation and swelling of the material. Very easily done with automated software. You would not be able to do this with, well, any other method. Another way where measurement can really help you, or another topic where measurement can really help you, is understanding the grain size distribution that you well, produce. So, without having an audience here, but I think many of you probably had a mineral processing lab. You have been sieving a lot and analyzing grain size distributions. You can't do that on a macropile. Well, you would need a cohort of students, and all the mining engineering students of 1 year of the entire world to sieve this material. And that's not really possible. So you want to have an automated software. And what you can basically see here is 3 pictures of the same thing. But on the bottom side, how different software solutions see this picture and how they analyze the grain sizes, because these software solutions, they rely on edge detection. So they detect the edges of the grains, and with that, they come up with a grain size distribution, a surface representation of these grain sizes. And this is, put it carefully, this is dangerous, or this is not extremely precise. So the idea is, of course, also here to come up with better solutions, more precise solutions. And those more precise solutions, they work like you see here on this picture with the jet planes and the people in front of this jet plane. So the software really automatically recognizes, is it a person or is it a plane? So it doesn't really rely on the edges, it relies on the form. It knows what is a plane, what is not, like the human brain also does. The human brain doesn't have to analyze the edges, the human brain simply knows. Because of training, of course. And you can do a convolutional neural network training there. And with that, you know that this is man or woman, I don't know exactly, and this is a jet. The same thing also works for grains. So what you can see here is the back of a dump truck, and you see all those yellow lines. This has been students' work. So a student was sitting there annotating all the grains, saying this is a grain, this is a grain, this is a grain, this is a grain. But when you do this often enough, the software learns. And in the second step, the software identifies the grains. What you can see here, for example, the other training data has not been enough. You can see that the software also recognizes the body of the dump truck. But when you do it regularly and repeat the exercise and with more and more training data, the software is really becoming more reliable and really knows what is a grain and what ain't. And you come up with quite good pictures. And I think this is a very good example. You just see the body of the dump truck once here, and you see 1 or 2 little mistakes here in the backside, which are kind of, you can't see that here, but there are some shadows in the picture, but the rest is really good representations of the grains that are actually lying on that dump truck. another example of the results. It looks a little differently, but so the interpretation is still, not exactly precise, but going into the right direction. It's my passion, but it also shows you something about the system. So probably when you're sitting at home and watching this video, you can pause for a minute or two and consider what makes the system fast. Why is the cyclist so fast? And that's also what we have to consider in a mining systematic approach. So we have to combine bits and pieces. We have to take care of what is actually helping our system, and what is, of which parts do we not have to take so much care. So many of you will probably say this makes the cyclist fast. But it's also the tires, it's the shape of the wheels, it's the position, it's even the structure of the skin suit that the guy is wearing, or the structure of the special shoes, which are friction optimized, so that they don't oppose any resistance to rolling forward. So with that we go into the systems analysis, and I'm going to show you a couple of small pictures now, but I hope that you can see them on the video. I focused during the last 25 or so minutes. I focused on this part, the blast site, in the mining operation. But as you are aware, the blast site is influenced by the geology. Geology can be very different in different blasting sites. Then, you can assess the geology by, as I have shown, by UAV drone measurements. You can assess the geology slightly by measurement by drilling, so that you measure how your drill rig is operating, which forces are applied there. A second very important part is the boreholes. So where are the boreholes spaced? What's the diameter? What's their precision? What's the alignment with the face? Also, this is something that goes into the blast site. That's the part which I've been focusing on during the last 20-25 minutes. Then, the result of the blast is the muck pile, also something that I've shown earlier. So the muck pile, you can assess the muck pile also with the drones, with the UAVs. You can take pictures, you know how the shape is. That's what I've shown a bit previously. But then comes the complicated, the tricky part. You want to know something about the loading. You want to know how the loading operation and the equipment is working. You want to know something about the hauling. And you want to know something about crushing. So how does the blast site here, how does it connect with the crusher? What's the influence in the crusher? And that's also what I wanted to show with the cyclist. So it's not just the legs that make the guy fast, it's the entire system that has to work together to make everything fast and reliable. And last but not least, of course, you want to derive conclusions. And I've just plotted some arbitrary numbers here, but you could, for example, compare the kilowatt hours per ton that you consume in the crusher with the time you take for loading, or the kilowatt hours per ton with the geology, type of geology, or with X50, so the grain size distribution, or with any measurement by drilling parameter. So there's many things that you might want to compare, and many things that you might want to analyze in the end. But first of all, you have to build this chain from the blast site to the muck pile down to the crusher to know what you're going to expect and what you really influence there. And as we're talking about measurement in this talk, I titled this slide with potential hiccups. Because when you talk about measurement, you always run into, not always, but I can almost guarantee that you run into problems. Most simple things, the format of the data, or the timestamps. Somebody's working in UTM, somebody's working in local Austrian time zone. The size of the files. Sometimes, a file is just from midnight to midnight, the other file is from midnight to 6 a.m., from 6 a.m. to 12 a.m., to noon, from noon to 6 p.m., and again to midnight. Then different annotations. Somebody types in track 01 versus track 1. It will have a dramatic influence when you it will have a dramatic influence when you code that and when you want to compare those two to one another. Different data formats, of course, as well. So you have qualitative data where you really have data, and you have quantitative data. Especially geology is quantitative. In many cases, you don't have one value for geology. You have an interpretation. You have something that you can't exactly put into numbers or push into numbers. So that's one of the tricky parts. Well, then, just showing you some field work of how we did that. So this campaign, you see two students here who are measuring drill holes deviation. You're seeing, well, more students doing the UV measurements and, well, some nice scenery in the Austrian Alps. What I want to show you also is we made a little test on different blasting parameters. In this video, I want to show you a set of parameters that we changed in a very interesting way, because we tried to combine two different blast sites. One would be here, and the other one would be here. So this is with a bit of a distance. And the idea was to make the seismic waves of these two blast sites overlap in the far distance in order to mitigate vibrations for the people living in the vicinity of the blast. So I'm going to show you a short video on that. So as I said, take a careful look at this area here. So that was the idea. Now comes the problem. Somebody's asking you, what does this actually mean for the mine? You can measure the vibrations, that's one thing. But you change the blasting layout, we change the delay timing, we change the type of explosives. So what's really the difference in this and that? Does it make it worse for the mine? Do we make it better for the mine? Should the mine bother at all? So that's one of the tricky parts there, and one of the tricky questions. That's why I'm going to go into a bit more detail on that in the upcoming slides. So number one, of course, peak particle velocity, which would be the vibrations. So what we did in this campaign, you see a map of the mine, an idealized map of the mine here, and you can see many black spots. And all those black spots are positions of geophones. So what we have there is 80 something geophones to observe, I think 35 blasts that we did there. And now we have the data of all those blasts and know how the blasts behave and how the vibrations of these blasts behave. That's, well, the most important part, the crucial part behind that. Then another very tricky part is, as I said, you want to know something about loading, you want to know something about hauling, crushing energy consumption, and so on and so forth. And this would be the good old-fashioned way as we did it, well, until 2 years ago. We still have a couple of students. We can position them in the mine. We give them a stopwatch and a sheet of paper, and we tell them, well, now track the operation. But you would have to know that this operation is working 24/7. They have 4, sometimes 5 different wheel loaders in operation simultaneously. And these wheel loaders change position quite regularly. So they don't always muck at the same position because that's a matter of quality control. So they want to move to other places and back and forth. So those students would have to run rather quickly or move around rather quickly. And still you would need plenty of students in order to follow the entire operation, which simply is not possible, and you can only get a glimpse of it, but not everything. So the second option that we have been thinking of is, well, this mine is operating with wheel loaders, and we could position time-lapse cameras here on top of the wheel loader. That's what you see in this picture here. When you take a look at this picture, that's what the time-lapse camera sees. So the time this camera takes a picture every second. With this picture, you know what the wheel loader sees. That makes the process easier because you can take the card, the memory card from this camera, bring it to your office, and then analyze the pictures in your office. Fast forward, that's much better than just standing and waiting for the next truck to come, the next truck to park, so the spotting, parking, dumping of the material. So in this case, you can speed up significantly. Still, you would have to have somebody in your office who takes a look at the pictures and analyzes the pictures. And she says, well, at 4 p.m., the wheel loader driver was heating the muck pile. At 4 p.m. and 30 seconds, it was moving away from the truck. 45 seconds, it was moving to the truck again. So that would be still a huge effort, but quicker than what you have seen previously with the students standing in the mine and documenting everything. And with this you can cover almost 100% of the mining operation. I say almost because, well, batteries are not always stable, memory cards are not always stable. And there's one thing that I want to highlight here, and that I need to highlight here, is you have to talk to the people which are sitting there. Because they also want to know what's happening on top of the cabin. They want to know what you track there, what you do with the data. So during this campaign, we made, well, a little mistake because we did not inform the people properly enough. And in the beginning, we had cloth on the camera. One of the cameras was losing the battery overnight. And I can't imagine how it would fall out there. So the people have not been involved properly in that process. And that's something that we had to learn very quickly. And then after we told all the wheel loader drivers what we're going to do with the data, what we're going to do with the systems, they have been good. And we did not have these incidents anymore. But then the truck drivers came and said, okay, on this video you also see us. So what do we do with our data? So we had to integrate the entire mine very properly into that operation and into that feedback. But that's just a learning that you also have to take whenever you deal with data and whenever you deal with that information. And then last but not least, because this is still not the end of the game, there is one more system which is based on mobile phones. That's what you see here. This is a mobile phone, like you and I. Oh, I don't have mine with me. But like you and I have in your pockets. And this mobile phone collects all the essential data that you need. It has your position, and it has sensors for your acceleration. It knows when you're moving forward, backward, left, right, or when you're moving up and down. And that's all the information that you need. And when you position a mobile phone like that, in all pieces of equipment, so in the tracks, in the wheel loaders, in everything that you want, you need, you can quite conveniently analyze the entire mining operation. And that's then, for example, how this might look like. What you see is here is the sensor of a loader, and this is the sensor of a truck. And let's start with the truck first. You can see that the truck is moving fast, slowing down, moving a bit again, and coming to a halt. So that was the truck coming, spotting, waiting for the wheel loader to be free, moving backwards, sitting there, and now not moving anymore. But what you can also see is the yellow line, for example. Yellow line would be acceleration in Z-axis. So when the first shovel of the wheel loader is dumped onto the truck, you can see that there's acceleration happening and that there's something happening. When you take a look at the same time from the wheel loader, you can see the wheel loader is waiting, and at some point it starts moving. Forward, backward, stopping, forward, stopping, backward. So that's going into the heap, going out again, going to the truck, dumping the material on the truck and doing the entire operation again and again. And when you have the combination of those two, and you have also the GPS coordinates of those two, you quite easily know which truck has been loaded by which wheel loader at which time. And very importantly, for what we wanted to analyze, how long does that take? So how long does it take to dig the material, to move the material to the track, and to load the track. And with that data, we can now infer information about the blast site and about the mining site. So how does the mining site deal with the new blasting geometry? What's the influence of this blasting geometry on the mining site? Additionally, of course, we also know when the truck is going to the crusher somewhere down here. So when does the truck go to the crusher, and what energy consumption does the crusher have based on all these events? And we can link the blast site, we can link the coordinates of the blast site with the energy consumption in the crusher, and of course also the geology and the lithology and the type of material that is going in there. And then the tricky part. What would you like to find out? Imagine you are the responsible mining engineer. What do you want to find out with this data? Do you want to find out when does the wheel loader driver make a break? Or where does the truck driver go for a pee? Or how long do they take for mucking? How long do they take for preparing the muck pile? Well, there's lots of information that you can infer from this data set, and what I can show you now is just what we analyzed and what we inferred for our information of our data set. But of course, every operation will be slightly different, and every operation will have different requirements, which they want to analyze and know more about. And this is, well, purposefully you don't see too much because it's also sensitive information. But I hope that you understand the idea of this graph. So these are box plots, and as I said, there are 4 to 5 different wheel loaders in operation in that mine. I displayed the 4 most important here, and you can see on the box plots how long the digging takes. How long does the wheel loader driver take to simply dig the material from the face? And you can see starting from point something seconds to maximum or something with 30 seconds here, 35 seconds. So what we, for example, found out is very appalling, that it's so much depending on the wheel loader driver, but of course also very much on the geometry, and even more on the geometry of the wheel loader driver than on the grain size distribution. So the grain size distribution, something that we wanted to find out with this field work, is not so much depending. So the loading capacity is not so much depending on the grain size distribution than it is on the general geometrical influences that you have there. But what you can also find out, for example, that this is a map of the entire mine site, and the spots, for example, they show. You can color them in any way that you want. But the spots, these spots could then show the energy consumption in the crusher. They could show the digging duration. They could show the type of material. They could show the iron content. They could show a combination of all of them. And then you know, okay, in this area, most of the things are colorful. Could be a deviation. In this area, everything is green or yellow or whatever color coding you have, and you can start to dig into the data, analyze the data, and investigate all the findings that you have. By the way, these are roughly 16,000 different truckloads that we analyzed there in just a month. So imagine having the students there clocking the situation. With this automated system, it was much better and much more convenient for us. What you could also do, for example, is a histogram like that. What you would see here is the kilowatt-hour consumption per ton in the crusher, and yeah, the number of truckloads from different locations. So that's the color coding with different energy consumption in the crusher. So you can come up with all kinds of different analyses there. Well, the analysis that I like the most from our campaign that I'm presenting you is that one. Any guess why? Because you don't see anything. So we wanted to see, for example, this was kilowatt hours per ton, and this other way around. This was kilowatt hours per ton, and this was the time you take for digging the material. So the theory would say the finer material is, the easier it is to dig this material, and the less energy this material consumes in the crusher. And the coarser material is, the longer, the more complicated it is to load that material, but also the more energy you consume in the crusher. So theory would expect a line like that, like the blue one here, or like the pink one. We don't exactly know the inclination. But we have negative trends, we have neutral trends, we have positive trends. Well, you can write me an email afterwards if you have a solution for that. We did not yet have a real solution to that. So theory is not so easy, I would say. Well, or something, or a dashboard like that, where you summarize all the data that I've previously shown. So you can show many things, you can analyze many things with technology. One of the things that I have recognized during this work, for example, was that we do have a lot of data here, but you have to make the best out of the data. Just sitting on the data doesn't make any value. So the title is this talk is entitled "Improving the Mining Performance by Measurement." But if you just measure and don't make any conclusions from that, yeah, you're sitting on a cemetery of data, but nothing else. That's not what you want to achieve there. But you can, well, have reasonable discussions and reasonable conclusions from that. So, coming to the end, I would say that most important here is the blast design process and data and real knowledge about the geometry, the geology, the rock mass, the drilling currency really helps you designing your blast and really improves your blast. Secondly, well, this design process and this knowledge has to be implemented in any explosive layout, in the optimum energy input, in the optimum fragmentation control. Well, yeah, you have to know the data to organize that and to come up with the best result for your operation. As well, the best result is not the same for all operations. Some operations probably want to have very fine materials. Some operations want to have coarse material. No operation wants to have vibrations. No operation wants to have too much noise in the vicinity. So it really depends on your personal or the goals of your operation, what you want to achieve, in which direction you want to move. But what is really very important here is also that with this automated process recognition, we can now really analyze the effects of different blasting setups, the effects of different input parameters, not just blasting. You can change many things in the mine, but with that we can track the input parameters downstream and really know what's happening. Well, last but not least, my contact details on the last slide. As this is a very virtual lecture, don't really know how we're going to have this discussion, but you can always give me a call or try to write me an email. And I believe that we also have an online session for 50 minutes, half an hour in course of this Dubrovnik International Mining School. I'm looking forward to the discussion there, the lecture there. Very frankly hope that I will be able to give another lecture in 2021, but physically and not virtually anymore. Thank you very much.